Hey there, fellow Moodlers. We're going to look today at Lewis dot structures. The first thing, to determine the number of valence electrons, we're going to look at the group number. If you're in an A group, that number corresponds to the number of valence electrons, which are outer shell electrons. So for example, the top of your notes here, let's start with just a group 1A element like potassium. Since it's in group 1A, it has one valence electron, so I would just simply put one dot around potassium. And you can use dots or you can use X's or any symbol you want to. Another example on Lewis dot structures at the top of your notes, let's say I have aluminum. That is in group 3A, so it's going to have 3 valence electrons. And we'll just kind of put those valence electrons around just something like this. Let's move on to one in group, let's say 5, like nitrogen. It's in group 5A, so it has 5 valence electrons. We're going to put one on each side. And then that 5th electron we can put on any side we want to. Just pair it up, something like that. The most you can have is 8. So if I'm in group 8A, let's say I have argon, put the symbol for argon. And it's got 8 valence electrons because it's in group 8A. So the most you can have, as far as valence electrons, which are outer shell electrons, is 8. And you simply look at the group number to determine how many valence electrons you have. If you're a B group, let's say iron, everything in the B group has 2. So iron would have 2. It could be anything in the B groups. Titanium would also have 2 valence electrons. So that's it for the Lewis dot structures. You simply look at the group number, and that's going to tell you how many valence electrons you have. Now, all atoms want 8 valence electrons. They don't start off with 8, as you can see right here. Most of them do not have 8, but they want 8. So we're going to draw Lewis dot structures for compounds, and we're going to ensure that all atoms normally get 8 valence electrons by sharing electrons with other atoms. And so when we do these Lewis dot structures, we're talking specifically about nonmetals. Now the instructions for drawing Lewis dot structures, I put them there on your notes for you. Number 1, arrange the elements with one element in the middle, surrounded by the other elements. Hydrogen has to go on the outside, and hydrogen only gets 2 electrons, but every other element gets 8. We're going to start from the outside and work towards that central element. The central element can have less than 8 electrons only if it's boron or aluminum, or it can have more than 8 electrons, but the outside atoms must have 8 electrons. So let's look at some examples here. The first example I have on your notes is Br4. So when we put the elements in order, there's only one carbon, so the carbon's going to go in the middle. And we're going to surround that by, in this case, 4 bromine. So the central element, you know what's in the middle, simply because there's only one carbon. So we're going to put that in the middle. We're going to work from the outside and go towards the middle. What I mean by that is we're going to start in the bromines, and bromines in group 7. So bromine has 7 valence electrons, and I'm going to use X's for the bromine. So I'm going to put 7 valence electrons on each bromine. Notice how I leave the single electron in between the bromine and the carbon. I'm going to do this for all of the outside elements. Because all of them are bromine, all of them have 7 valence electrons. We know that the outside atoms want to have 8. They have to get 8. They want 8 valence electrons to be stable. Carbon is in group 4A. So what's going to happen is carbon is going to give one of its electron to this bromine. So this bromine right here now has 8 because it's sharing one of carbon's. Carbon has 4, so we're going to put one here, one up here, and one over here. And I'm going to circle those bonds. Those are covalent bonds. They're shared electrons. And I'm just using the different symbols to indicate where the electrons come from. So the X's are from bromine and the dots are from carbon. But if you look around each element, this bromine should have 8 around it. This bromine has 8. This bromine has 8, and the carbon also has 8. If you count up the shared electrons, the ones that I've circled are shared between the atoms, but every atom has 8 valence electrons, and that is ultimately what we want to accomplish. So let's look at the next example. It's H3P. Hydrogen, one of the rules is hydrogen has to go on the outside. So we know that phosphorus is in the middle, something like this. Hydrogen has 1 valence electron. We're going to put that one like right here. So each hydrogen is in group 1A, so each hydrogen has 1. If I can get those to stay. Okay, hydrogen only wants 2. It's the only element that wants 2. So what's going to happen is phosphorus, we'll give phosphorus the X's here, phosphorus is going to give 1 of its electrons to this hydrogen. So this hydrogen right here is good. Phosphorus is going to give 1 of its electrons to this hydrogen. So now this hydrogen is good. And phosphorus gives 1 electron to this hydrogen. So this hydrogen is now good. Hydrogen only wants 2. Every other element wants 8. Phosphorus had 5 to start. I've only drawn 3 electrons. I'm going to put the other 2 just over here as what's called a lone pair. But if you count up the number of electrons around phosphorus, there are now 8 electrons around the phosphorus, 2 around each hydrogen. So sometimes you get a shared pair. I've circled the shared pairs. Sometimes you'll get what's called a lone pair of electrons or an unshared pair of electrons around that central element. Okay, let's go to the next one. The next element is Pi5. Again, normally we have 1 in the middle, and we're going to surround it by the other elements. And in this case, there's actually 5 iodine. So we're going to put 5 iodine around the phosphorus. We're going to start on the outside and work towards the middle. I is in group 7, so we're going to put 7 valence electrons around each iodine. Notice how I leave that single electron towards the middle so it can share with phosphorus. You would not want to leave a single electron out here, because if you left that single electron right there, there's no way that electron's going to pair. So I always put the single one towards the middle so it can share with the central element. Okay, so each I has 7. It wants another one. Phosphorus is in group 5. So phosphorus has 5 valence electrons. We know each iodine needs 1 more. So phosphorus is going to share with each iodine, since it's got 5, and there are 5 bonds, 5 single bonds here. Phosphorus is going to share with each iodine in order to give each iodine 8 electrons. If you count around each I, there are 8 valence electrons, which is ultimately what we want. Now, the central element can have more than 8 if it needs to, and in this case it needs to because it's bonding with 5 different atoms. So the central element here has 10 valence electrons, and that's okay if it's in the middle. Your central element can have more than 8. So let's move to the next one, because this will kind of help with the next one, ARI2. AR, I's are going to go on the outside. We're going to start on the outside, work towards the middle. Each iodine has 7. And so each iodine needs 1 more. So we're going to share. Argon's going to give 1 to that iodine, 1 to that iodine. Now these are good. They have 8. But argon was a noble gas. It started off with 8 valence electrons. So actually it has 6 more left over. We're just going to kind of write those in pairs of 2 around the central element, something like this. And I always like to circle the ones around the central element. So argon, again, the central element, in this case it started off with 8, but since it's bonding with iodine, it actually has 10 valence electrons around it in the structure. But that's okay if your element is in the middle. Let's move to the next example. We have BF3. B goes in the middle, F on the outside. And again, typically the one that goes in the middle is the one that you just have one of. Well, there's one B, there's 3 Fs, so the Fs have to go on the outside. So we'll start on the outside. F is in group 7, so it has 7 valence electrons. Boron is in group 3, so it only has 3 valence electrons. But if you go back to the instructions, there are some elements, specifically boron or aluminum, which are going to have less than an octet. These are the only two that will have less than an octet. In this case, and in all cases, boron will have 6 around it, as will aluminum. Aluminum would only have 6 as well. Okay, the next structure, O2. Oxygen has 6 valence electrons. So we can put 6 X's around the oxygen. Now here's what I'm just going to start off with something that looks like this, but I'm going to show you why it's incorrect. This structure is incorrect. First of all, if you put a single electron out here, there's no way that can pair up to give each oxygen 8. So you really don't want to have single electrons on the outside like this. But what I have now, I have a structure that has 7 electrons around each oxygen. If you count up the number of valence electrons, there are 7 around each oxygen, but they want 8. So what we're going to do is we tried a single bond. We tried 2 electrons right here in the middle. Well, 2 electrons did not work. So we're going to make what's called a double bond. So if 2 electrons doesn't work, we make a double bond, which is 4 electrons. So we're simply going to move. I'm going to move this electron right there in the middle, and I'm going to move this electron right there in the middle. So I'm going to redraw this structure. And the correct structure for O2 looks like this. You have a double bond. This is a double bond. Those are 4 shared electrons, but if you count up the number of dots around each oxygen, you should get 8 valence electrons. Again, ultimately what we want, 8 valence electrons around each atom. So if a single bond doesn't work, you try a double bond. The next structure, H2C2. We know H has to go on the outside. So the order is going to look something like this. We've actually got the 2 carbons pretty much in the middle. We're going to start from the outside and work towards the middle. Hydrogen has 1. We're going to put that 1 right there. And we're going to put the other hydrogen right there. Each carbon is in group 4A, so carbon has 4. We're just going to arbitrarily place these valence electrons around each carbon. And see if this works. So if I do this, the hydrogen's good. The hydrogen only wants 2, and each hydrogen has 2. There's a shared electron here and a shared pair of electrons here. But the carbons only have 6. Each carbon only has 6. So a single bond didn't work for the carbon, so what we're going to do is try a double bond. What we can do is move the 2 dots. We can move those right there. So I'll redraw the structure. I made a double bond. I simply moved the 2 dots, And what I did, in essence, was I moved 2 dots off of one carbon, and this carbon now has 8 valence electrons. So that carbon's good. But this carbon right here still has 6. So making the double bond helped one of the carbons, but the other carbon still only has 6. So we'll try a triple bond. We can move these 2 valence electrons into the bond and make a triple. And I'll redraw the structure. The most you can have in between atoms is 6. That's called a triple bond. This is a triple bond right here. Those are 6 shared electrons. But by making that triple bond, I've given each carbon, if you count up around each carbon, there are 8 valence electrons, which is ultimately what we want. And again, the hydrogen only want 2, so they're good with just 2. So the structure looks something like this, with a single bond between the hydrogen and the carbon and a triple bond between the carbons. That last example, I have HCN, and it's written just like it should be drawn out. Again, kind of start from the outside and work towards the middle. Hydrogen has 1 valence electron. Nitrogen has 5. It's in group 5A, so we'll just draw 5 valence electrons arbitrarily, and carbon has 4. It's in group 4A. Again, I'm going to try a single bond first, see if that works. Hydrogen's good. It only wants 2. It has 2. The carbon, however, has 6, as does the nitrogen. So if a single bond doesn't work, we try a double bond, and we simply move electrons. And you can move any electrons you want to try. So let's say we want to move these X's right here into the bond, and we'll try that. Again, don't mess with the hydrogen. The H is good, so don't mess with those electrons right there that I've circled. So I made a double bond. What happened was the double bond, it actually helped carbon. So moving the electrons from nitrogen helped carbon. It gave carbon 8. But the nitrogen still only has 6. And again, we want everything to have 8 to be stable. So if a double bond doesn't work, then we try a triple bond. And a triple bond, we'd move the electrons from carbon right there in between the bonds. And so my structure will look something like this. There's a triple bond. That's a terrible N, but there's the triple bond. There's a single bond. Hydrogen has 2. Hydrogen is the only element that wants 2. Everything else, if you can, make sure that they have 8 valence electrons. So there's a lot of trial and error to this. Get the order of atoms. Start from the outside and work towards the middle. Sometimes you're going to have to make a double or a triple bond in order for the structure to work.